Hello everyone. In our previous video, we learned about three measures of center, the mean, median, and the mode, which uh, basically help us determine a typical element in a given data set. Uh, and today, what we want to do is we want to learn about some measures of spread. So we want to know how spread out the set of data that we're looking at is. And that's what we're going to talk about today. As I said, we call these measures of spread. Before we get into the actual discussion on measures of spread, I thought it would be good for you to have a big picture of what it is we're actually doing in the class. Um, First, we learned about these measures of center, right? Mean, median, and mode. Then we have measures of spread, right? Which tell you whether the data is really spread out or kind of tightly packed together. And we also have seen measures of symmetry with respect to skewness. And we are also going to learn a new measure of position called the z-score later on. But we've already seen percentiles. We're going to get into more detail about percentiles in this chapter as well. So this is kind of the overview of what's going on. The first and the simplest measure of spread that we're going to talk about is just the range. So you're given a set of data, it could be any kind of a set. For example, something as simple as say 2, 5. I'm just going to sort them 8, 15, and 22. Okay, so the range is the simplest possible measure of spread that you can get, because all you're going to do is you're going to take the largest observation and the smallest observation, and you're going to subtract them. So here the range is going to be 22 minus 2, which is 20. And it's a very quick way to get a feel for what the set represents, what kind of numbers are represented in the set, and how spread out they are, right? Mainly the spread is what we're interested in at this point. So here we have a quick example of finding a range, and this table represents vehicle sales in April of 2014, and we can see the sales of General Motors, for example. There were 254,076 cars sold. Chrysler sold 178,652, etc. And you can see on the lower end we have like Volkswagen at 46,715, on and on. So if we want to find the range, we need to locate the largest and the smallest value. So if this is a very large set, of course, we'll utilize technology and we'll sort the data so we can easily determine which one is the largest and which one is the smallest. But this is a real simple case and not that many numbers. We can easily see the number in the red is the largest max value here, and this is what we call the minimum or the min value. So basically we're going to subtract and get the range. So when we do, we end up with 213,993 vehicles for the range. So what does this suggest? This suggests actually that the spread of vehicle sales in the auto market is quite wide, and there's a very large spread. So that means some automakers sell quite a lot and some automakers sell quite a few compared to the ones that sell the most. It's important to note that the range is not the most reliable measure of spread. For one thing, it is not really resistant to outliers. So we will learn about a different kind of range later on. It's called the interquartile range, which is much more resistant to outliers. So that one we will prefer to this range. This range, which is just the maximum value minus the minimum value, is just great for just a very quick, measurement of the overall spread. It doesn't get into fine details of the spread. We'll find better means of doing that soon. When it comes to distributions that are almost normal or completely normal, and that actually happens to be a great number of distributions we will encounter in daily life. For all those, there's no better measure of spread than what's called the standard deviation. And basically, what we're going to do is we're going to find, for a given data set, running from x1 to xn, we're going to find the mean. Remember, x bar represents the mean of a sample, and we're going to find the distance between each of these data points and the mean. We're going to square those distances, then we're going to add them. Remember what this notation here means? It means the sum of all such entities. So just to spell it out a bit, right? So for example, you will get so let's see what that means. So that means first let I be 1, so we get x1 minus x bar squared plus, then we're going to let I be 2, x2 minus x bar squared plus, and we continue this all the way up till we get to x5. So the dot 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 means just keep doing this with x3, x4, etc. And the last one will be x5. Well, I'm just using an example with 5, or if you want to just stick to a more general n, we can just say xn minus x bar squared. That's what this means, okay? And then we divide that by n minus 1. This is actually the definition of standard deviation for a sample. This is the only type that this particular textbook and this particular my Math Excel or my MATLAB module handles. But as you get into a regular statistics course, you will also learn about the standard deviation for a population. And whereas here we use lowercase s to represent the standard deviation, for a population we use this notation. You could do better than that. Looks kind of like so. No, I can even do better than that. It's kind of it's a Greek symbol, and we call it sigma. So but we won't be using that in this class. Again, once you get into a regular statistics course, you'll see that as well. So just so that you don't go, whoa, what's that? I'm just kind of like giving you a preview of it, that's all. The procedure is actually quite simple. What's really important is to understand what we're doing here. First of all, why are we squaring, right? Well, because basically if we only took the distances from each data point to the mean, some of those distances may end up those differences, sorry, not distances but differences, some of those differences may become negative, and then we may not want that under the square root, right? So in order to avoid that and to always make sure we get positive results, we actually square the distances of the items, all the data items from the mean, and then add them. But to compensate for the fact that we squared, at the end we take the square root. So that's what we're doing. So one way that people like to think of the standard deviation is that it represents kind of the average distance from the mean. All right, so given a distribution, we want to know what's the average distance of each data value from the mean, right? So the average of all those distances for each of these data points. All right, so and remember, this does give us a measure of spread. So the larger this value becomes, the more spread out the particular distribution of data that you are looking at is. Now, standard deviation is a rather tedious process. It's very simple. There's nothing to it as far as the arithmetic is concerned. Not that difficult, except it's just kind of tedious. There's a lot of steps involved, right? So what we like to do is run through a couple of them by hand so that we make sure you understand how to do it, and then we'll let technology take care of it for us, okay? But it is important to understand what it is and get a feel for it. So here's an example for the levels of cholesterol in the equivalent of 1/8 of a 14-inch cheese pizza from several different pizza companies, okay? We want to find the standard deviation of the cholesterol levels, and here they're just mentioning that since even though California Pizza Kitchens is 5 cheese plus fresh tomato, it's being included because tomatoes don't actually add any cholesterol. So it shouldn't really throw off our data. All right, so here is the really simple small set of data that we have. Remember, this is the equivalent of 1/8 of a 14-inch pizza, right? So you take a 14-inch pizza, you break it into 8 parts. This is going to be how much cholesterol there is in one of those slices, right? So for Pizza Hut, it's 30 milligrams. For Little Caesars, 20. For California Pizza Kitchens, of course, it has 5 different kinds of cheeses. You would expect it to be on the high end, 41. And Papa Murphy's, 21. All right, so let's see what we can do with these. First thing we need to do, remember, if you go back to the standard deviation formula, let's do that for a second. Remember, the first thing we need to do is find the mean. Remember, that's just the average. So we're going to add all the different data values and then divide by the number of items, which in this particular problem, I believe it was 4. So let's go back. So remember, the mean is the sum of all the data items, right? Data values divided by the number of data values, right? In this case, it's 4. So we just get 28. So the mean cholesterol level for the group was 28, right? So now we're going to find the, remember this expression right here, and the square of it, right? This difference, by the way, is called the deviation score. Not a particular value that we're going to be using quite a bit on its own, but it's significant in the computation of the standard deviation. And then this is just the square of the deviation score. So the easiest way to do this is just go ahead and make a nice table. Here we'll list all the different data values. Next to it, we'll put the mean. Of course, they're all the same because it's the same mean for the same group. And then here we'll just write the deviation score, right? Each data value minus the mean. Now remember, you're going to always do it in this order. So data value minus the mean. The mean comes second, right? And notice how some of them become negative. Now you see why we need to actually go ahead and square. So after we find these deviation scores, we'll go ahead and square them like so. And we, at the end, just go ahead and find the sum of the squares, right? This, by the way, does always tend to come out as 0. It's actually easy to prove, but we won't be dealing with that kind of proof in this class. So here, we'll just go ahead and take this sum now and just plug it into the standard deviation formula. So remember, the standard deviation for a sample is the square root of that sum divided by n minus 1. What is n? N is just the number of items in the data set. So in this case, it's just 4. So here we get this, and we get approximately 9.7639, which we can round to 9.8. That is the standard deviation for this particular example involving cheese pizzas and how much cholesterol is in a slice, which is 1/8 of the entire 14-inch pizza. This next example is going to show us that the standard deviation is going to be a powerful way of comparing two different distributions. So a household is said to suffer from food insecurity if at some point in the year the household either eats less, goes hungry, or eats fewer nutritional meals because there is not enough money for food. The percentage of households suffering from food insecurity are shown in the table on the next slide for the West, North Central, and Pacific states. So here are the data values for the West, North, Central states, and these are the ones for the Pacific states. All right, so we want to find the mean and standard deviation for the two groups. Now, we have done so using technology, and again, I'm going to show you how to do that once we're finished with the lecture through some examples from the homework. But for the time being, just take these values to be true. So the mean is 12 point, approximately 12.7 for the West, North, Central states, and the standard deviation 2.98. For the Pacific states, the mean is higher, see, but the standard deviation is much smaller, notice? So the spread in the Pacific states is much smaller than the spread for the West North Central states. And we'll see that in a minute in a nice graphic. So basically what this means is that when the mean for the West North Central states, which is 12.67%, is certainly less than the mean for the Pacific states, right? So West North Central state tends to have a lower percentage of households with food insecurity, right? Because on average, it does better. However, the standard deviation for those states is more than twice the standard deviation for the Pacific states. So the spread is much larger than it is for the Pacific distribution. And you can see that beautifully in this dot plot that we have here. So on the bottom, we're showing the Pacific states, right? And on the top, you're seeing the spread for the West, North, Central states, right? Notice a very different kind of distribution. This is very spread out. These are all packed very close together. In fact, notice that even though the West, North, Central states had a smaller mean, notice that one state had a percentage higher than any of the Western states, okay, or the Pacific states, I mean. So this is a very nice example showing you how standard deviation shows you the measure of is a measure of the spread between for a distribution, and it allows for really nice comparisons between two different distributions. Now, there's a really important and really significant rule called the empirical rule, which applies to distributions that are unimodal and symmetric. So pretty much the bell-shaped curve that you're familiar with from news stories, etc. Then here's the empirical rule. What it says is that approximately 99.7% of the observations, that means what? That means pretty much all of them, right? Lie within 3 standard deviations of the mean, right? So, and we're going to look at some really nice graphics in a minute. So basically, approximately 99.7% of the observations lie. Remember, when we say within 3 standard deviations of the mean, so we mean the mean either plus 3 standard deviations and the mean minus 3 standard deviations, in that range, okay? Again, we'll see a beautiful graphic of all this in just a second. Right there. So this is what the empirical rule actually says. It tells us other stuff as well, but the most significant is the first part, that look, if this is the mean right here of the distribution, almost all the observations within that normally distributed set of data is going to fall either basically within 3 standard deviations. So that means either 3 standard deviations to the right or 3 standard deviations to the left, right? So now, if you want to get a little bit closer, so 2 standard deviations away, within that 2 standard deviations, you're going to catch 95%. So that's actually really significant too. So if you just go 2 standard deviations to the right and 2 to the left, you'll actually capture 95%. So that right there will represent 95% of all your data values. Remember, only if the distribution is normal and unimodal. Now, if you just go 1 standard deviation away, right, in a normal distribution from the mean, and remember, in a normal distribution, the mean, the median, and the mode, they're all the same, right? So if you go 1 standard deviation to the right or left, within that region, you'll capture 68% of all the observations. So basically, what it tells you is that when you have an distribution which is normal and also unimodal, right, then the data is packed in together pretty closely, right, just like this. So just 1 standard deviation away, you're going to catch 68%. of all the other data values in the study. If you go 2 standard deviations, you'll capture 95%. And if you go 3 standard deviations, you pretty much capture everything, right? Except for a very small amount on the tails here. All right. Here's an example regarding the Wechsler IQ test measures. Basically, Wechsler showed that human intelligence is normally distributed. The mean is 100, so that's the mean human IQ, and basically the standard deviation is 15. So one standard deviation to the right of the mean human IQ will be 115. One standard deviation will be 85. That's just 100 minus 15. And on this side you have 100 plus 15. So 2 standard deviations will be what? You have to add 2 15s, right? Because the standard deviation is 15 points. So 130 on this side, and if you subtract 30 from 100, you get 70. And then you go to 145, and on this side you'll end up with 55. So basically 99.7% of IQs, of course according to the Wechsler measure, right? Somebody else may have a different measure type of test and measurement, which may produce different results. But for the Wechsler IQ test, you're going to get 99.7% of intelligences somewhere between 55 and 145. Okay, the average being again 100. Now the majority, so remember, 2 standard deviations, you capture 95%, right? So 95% of all humans will have IQs between 70 and 130. 68% will have IQs between 85 and 115. All right. So this is why you can see, both of these would be considered very extreme, right? Remember, anything more than 2 standard deviations away from the mean in a normal distribution is considered to be an unusual score, right? So anyone scoring above 130 or less than 70 would be very unusual, right? So here you're probably looking at some kind of a mental problem, and over here you're looking pretty much toward the genius zone, right? Okay, so if you want to estimate M, remember capital M stands for the median. And for a normal distribution like this, remember the median, the mode, and the mean are all at the same location right here. So 100 will be the estimate for the mean and the median, right? Both of them. So because remember, the mean and median will be the same. M stands for median, and X bar here stands for mean. And the standard deviation, of course, remember, since these two, this is a density histogram. That means the areas of the bars represent the relative frequencies. So since we have 0.34 and 0.34, so that means 0.68. Since one standard deviation away from these would capture 68%, we estimate the standard deviation to be 15. Okay? And all that is just reiterated here, what we just discussed. All right, so next we want to go ahead and see if we can determine whether an observation is unusual or not. Some songs played on a particular radio station, Live 105, on April 18, 2014, have song lengths with a mean of 232.9 seconds. Uh, think about it. If you have 4 minutes, that's pretty much 240 seconds. So a little bit less than 4 minutes, right? The mean of the song lengths on that particular station, and the standard deviation of 49.6 seconds. One of the songs is Lazy Eye, which lasts for 354 seconds. Is the song's length unusual? All right. Now, we know that the song lengths between 133.7 and 332.1 are within 2 standard deviations of the mean. So why is that? Because look, you have the mean is 232.9, right? And so we're going to go ahead and add 2 standard deviations to it. So 2 times, remember the standard deviation is 49.6, so we get 332.1. That's where this upper bound comes from. And if we take the mean again, and subtract 2 standard deviations from it, we get 133.7. All right, so now this song Lazy Eye lasts 354 seconds, so it's more than 2 standard deviations to the right of the mean, right? So it's longer than the mean song, right? The length of this particular song is longer than the mean song value, which was 232.9 seconds, by more than 2 standard deviations, right? So it's going to be outside of this interval from 133.7 to 332.1, which covers 2 standard deviations from the mean, right? So therefore, we conclude that the song is indeed unusual. To be unusual, you just need to be more than 2 standard deviations, either to the right or left, right? Either greater than the mean by more than 2 standard deviations, or less than the mean by more than 2 standard deviations. We're going to formalize this notion of unusualness and eventually get to the notion of outliers very soon. All right, so to summarize what we've learned about measures of center and spread, basically if a distribution is unimodal and symmetric, you know, pretty much the bell-shaped curve, then we usually go ahead and use the mean to measure the center and the standard deviation to measure the spread. If it is skewed, we actually prefer to use the median to measure the center, and the range for the spread, until we learn about the better type of range that I told you, the interquartile range, which we will get to very soon. Now, the notion of variance is another type of measure of spread, but it's nothing new. You already know the standard deviation, right? Variance is nothing but just the square of that. It's not a measure we use that often, but for the sake of completeness, I'm just going to mention it to you. So, you know that in an earlier example, we did the measurement of the cholesterol for 1/8 of a 14-inch cheese pizza. We calculated the standard deviation to be that many milligrams, right? 9.7639. To find the variance, all you need to do is take the standard deviation and square it. That's it. You get the variance of this particular data set. Again, we don't use it a whole lot, but it's good to be familiar with the name in case you see it, you don't wonder what it is. All right, so now we're going to go ahead and look at some examples from section 4.2. All right, so here's a simple problem with numbers in millions of downloads of countries' top 5 most downloaded songs, and we want to find the range and standard deviation of the number of downloads. So notice that we should do at least 1 or 2 problems just manually to get a good feel for what the range and standard deviation are about, and then we'll go ahead and utilize technology. Even this problem, we'll go ahead and do it by hand first, and then we will I'll show you how to use StatCrunch to do the same calculations. Okay, so for the range, basically we need to go ahead and locate the largest of these values, right? So that would just be the 6.9, right? And subtract from it the smallest, which as we can see, it's the 4.4. And when we do that, we get 2.5. All right, so the range is 2.5 million downloads, and the standard deviation of the set of data, right? So let's go ahead and first find the mean, right? Because I'll write the formula here. You remember the standard deviation for a sample is the square root of the sum of xi minus x bar squared over n minus 1, right? So we would like to make that table. So in order to make the table that we looked at earlier, we'll go ahead and find the mean first. So x bar is going to be 4.9 plus 6.3 plus 6.2 plus 4.4 plus 6.9, and we divide that sum by, notice you have 1, 2, 3, 4, 5 numbers here, so by 5, right? And we end up with let's see what we get. All right, so we'll have to get out of that mode. So let's see. Oops, I didn't want to do that. Thank God for undo, right? All right, so 4.9. I grab my keyboard, it'll be faster. So 4.9. Actually, what I like to do is go ahead and put the entire numerator in parentheses. So 4.9 plus 6.3. You should definitely be doing this along with me. This is not a movie to sit there and watch. This is a classroom. So you should have paper and pencil in hand, and you should be doing all of this with me if you really want to learn this quickly. All right, so there's the numerator. Now we're going to hit divide by 5. So we get 5.74 for the mean. So x bar equals 5.74. Oh, I wrote that. All right. Let's make sure. Always like to check to make sure that I have put in the right data. So it takes 5 seconds, but it could save us 5 points, right? So 4.9 plus 6.3 is 6.2, 4.4, 6.9 divided by 5, and 5.74. Okay, good. Because if those numbers are wrong, everything is going to be pretty much problematic from that point forward, right? So so now we're going to make our table. We're going to have xi. We're going to put x bar next to it, and then we're going to do the deviation score, xi minus x bar, and then we're going to do the square of the deviation score, like so. Okay, so now it's just a matter of filling this table. So the xi, you do not have to have these necessarily in ascending order or anything like that. You could, of course. So we have 4.9, 6.3, 6.2, 4.4, and 6.9. Okay, now we know x bar is 5.74, right? So that's not going to change. That's just going to be the same x bar that you're going to subtract from each data value, right? So now here we're going to have 4.9 minus 5.74 and 6.3 minus 5.74, 6.2 minus 5.74, and 4.4 minus 5.74 and 6.9 minus 5.74. All right, so we could compute those separately and then square, but instead of doing that, I think we'll just be clever and we'll go ahead and just punch into the calculator. Also remember, down below, we're going to find the sum of all these squares of the deviation scores. So here's what we'll do. We'll just go into our calculator and we will do the following. We will go ahead and find the sum divided by n minus 1 and then take the square root, right? So we'll start with the square root, and on the top we're going to put, use my keyboard, so we're going to put 4.9 minus 5.74, and we're going to go ahead and square. and we're going to add to that the next difference, which is 6.3 minus 5.74, and then we're going to go ahead and square that, and then plus the next deviation, square of deviation score, so 6.2 minus 5.74 and then plus 4.4 minus 5.74 squared, and then plus, almost there, 6.9 minus 5.74 squared. And now we need to go ahead and actually we should have probably put all of that into another parenthesis. So let me do this. Let me go ahead and put that in a bracket. It'll be better. And now when we hit divided by, should stay under the radical. See, that's what you want. And down here, you're just going to put the number of items minus 1. So 2, 4, 5. 5 minus 1 is just going to be 4. And then and then you get this silly thing, which I'm not sure what it means. Give me 1 second. Okay, I think I just found out what the problem is. Desmos uses, this is a different calculator. It's similar to ClassCalc. It uses brackets for lists. So I'm just going to go ahead and put a parenthesis there, right? I don't even really need it anymore at this point, but like that. There we go. Okay, so there we have the standard deviation. If anything, doing these manually will make you really appreciate it, you know, when you get to do it with technology. And of course, when you round that to the nearest hundreds, you get 1.05, okay? And that's where that comes from. So remember the formula up here. Now, what you don't want to do is you don't want to do several rounds of rounding, right? So that's why I did it all in one shot, so the calculator just does one rounding at the very end. That's for maximum accuracy, okay? So when you have a process that involves several calculations, you don't want to do several different types of entries. You want to do one entry and let the calculator just do the rounding off once. You would definitely be selling yourself short if you didn't run through these at least once or twice manually, because then you start to get a real good feel for why you're doing this anyway. You're finding those distances. You realize, oh, okay, I'm just finding these distances between each data value and the mean, and squaring and taking the square root. So I'm basically pretty much finding the average distance from the mean, and it's very, very useful to do so by hand. So now let me show you how you could have used technology. So we're going to go ahead and open StatCrunch. It gives me this error every once in a while. I will just refresh it, and that usually fixes it. All right, so there's my data. Okay, so what we're going to do is we're going to stats, we're going to summary stats, and we're going to, of course, use a column. So we're going to push column. All right, now in here, you can tell it to give you whatever you want, right? So here I'm going to ask it to give me the number of items. I know it, but it's good to know how to do that. And I'm going to ask it to give me the mean and the standard deviation. And let's keep going down. I'm going to also ask it for the range to make sure I did that correctly too. I know I did, but we'll visit some of these items in the next section, okay? The interquartile range that I've been telling you about, very important quantity. But this should be good for right now, okay? So there we have it. Okay, so all that work that we just did, yes, technology can do it much faster, but let's face it, let's assume that we all just learn how to punch into a calculator, well, it is a calculator, you know, a statistical calculator like this, right? Can you guess what problem we'll eventually have down the line, right? Who do you think programmed this? The person who programmed this knew how to do it manually, didn't they, right? So we don't want a world full of individuals who can just punch into a calculator. Remember, we can take some chimpanzees, and given enough bananas, we can teach them how to plug, you know, punch stuff on a calculator and get it done. So the human aspect where we come in is actually being able to know the reasoning behind where these numbers come from, not just knowing how to take this and put it into StatCrunch and crank it out, right? You would be really, really selling yourself short if that's all you did. The reason I keep saying all these things to you is because you don't see it yet, but I see it, okay? Because I've been in the real world. It's a competitive world out there, okay? If you go out there where all you've done is find little clever ways of weaseling, out of, your way out of school and education, you're going to be in for a real shock. I don't want that to happen to you. You understand? You're my students and I care about you. So if I say all these things, trust me, it's nothing, it's no loss off of me if you don't do that for yourself. But it will be a great loss for you if you don't take maximum benefit of the educational opportunities that have been, become available for you. So make sure that when I say these things, you take them seriously, okay? Here, I guess you can see n, that's the number of items in the data set, that's just 5. The mean, as we found ourselves, is 5.74, and the standard deviation right there, round it to any level you want. And here is the range, 2.5. All right, let's look at another. Okay, so in this next problem, we have a group of students that were surveyed about their genders, their ages, the number of texts they sent daily, the number of hours spent working weekly, etc. The results are shown in a table. Determine the standard deviation of the number of hours worked weekly. So here is the data, right? Now, they only want the standard deviation of that number of hours worked weekly, right? So we're only going to be interested in this data, right here. But if you go ahead and open this in StatCrunch, it's not just going to bring you that, is it? It's going to bring everything. But that is no problem at all, because all we're going to do is when we go to stat, summary stat columns, we're only going to choose the work column, right? Because that's the one we want to get the various measures for. So we'll just pick And here they only want standard deviation, right? So let's just, we don't even really need n, so let's just find the standard deviation. There it is. Okay, and there we have it. So here they want it to the nearest tenth as needed. So to the nearest tenth, you have to look at the hundredths digit, right? That's an 8. That means you have to round, add 1 to the 9, which becomes a 10. So this becomes a 3. So that's where the 3.0 comes from. All right. All right, so here's a slightly different one. The author surveyed one of the statistics classes he was teaching. The number of units students were enrolled in are shown in the table to the right. So like this student was taking 16 units, another one was taking 10 units. This is just raw data, right? Use the table to complete parts A through E. Construct a histogram. All right, so again, histograms can be constructed by hand, but we will go ahead and, since that's a pretty large set, we'll go ahead and use StatCrunch. All right, so we want a histogram, right? So remember, graph, histogram, and let's make sure we know what kind of histogram they want. Yeah, when they don't say anything, they just say histogram. It's going to be a frequency histogram, okay? If they wanted relative frequency, they would have mentioned it. So if they just say histogram, you can assume that's just a frequency histogram. All right. So it's already the default. Now let's see if they want us to start at a particular, yeah, so we want to begin with a lower class limit of 4 and a class width of 2. So we're just going to put start at 4 and have a width of 2. And let's go ahead and put values above bar. That's always a nice thing to do because it makes it easier to read, and that should be good. Okay, so there we have it. When you say put values above bars, it shows you. So there were 2 in this class, right? 1 here, 8 there, 11, 13, etc., right? So we started with 4, remember? And the width is 2. So this is from 4 to 6. So there were 2 observations between 4 and 6. So 2 students were taking between 4 and 6 units, right? This is between, looks like it's between 8, right? Yeah. So from 8 to 10, the frequency is 1. So if you just kind of go to the corner here, it'll show you. So I didn't want to do that. So just right here, see, from 10 to 12. Notice including 10, excluding 12. That's why there's a parenthesis on the right of 12, bracket on the left of 10. That means including 10, excluding 12. So there were 8 frequencies that were greater than or equal to 10, but less than 12. Etc., etc. Okay, so of course when you come back here, you'll find only 1 matching yours, right? So here's the histogram, right? Make sure if there 2 of them are close, be very careful with the analysis, but here they're pretty different. So describe the shape of the distribution. Can the empirical rule be applied? If you look at the distribution, yeah, it is not a perfectly normal distribution, but it is what's considered to be symmetric enough. Okay, so because it is has only one mound and it's rather symmetric, we can use the empirical rule to kind of guess at the, determine the ranges that we talked about, between, like, within one standard deviation you capture 68%, within two 95% of the observations, within three 99.7%. Compute the mean, right? That should be easy. We'll go to stat, summary stats, columns, choose the column. If you don't select that, it's not going to do it for you. And we want the mean, right? So what else do they want? Let's see if we can go down. The standard deviation, yeah. So we want the mean and the standard deviation. Remember, you have to push, after you select mean, you have to push either control on a Windows machine or command on a Mac machine device to highlight more than one item. Go ahead and hit compute. So there they are. There's the mean, there's the standard deviation. So make sure that you pay attention to the rounding, round to the nearest tenth. So to the nearest tenth, which is right there, there's a 2 on the right, so to the nearest tenth it's just 13.0. And for the standard deviation, the same requirement, to the nearest tenth. This one, however, notice there's a 5 on the right of the 9, so you're going to add 1 to the 9, so this becomes 3.0. All right, so according to the empirical rule, approximately what percent of the observations should lie within one standard deviation of the mean? We know that. It's called, remember, one of the names for the empirical rule is 68, 95, 99.7 rule, right? So count the actual number of observations shown in the table that lie within one standard deviation of the mean. What percentage is that of the 42 students? The easiest way we're going to do this, right, is if we use a stem plot, right, to get the count, because otherwise if you're going to do the histogram, that just gives you ranges, right? So you're not going to be able to get an exact count. So we want to count the actual number of observations that are within one standard deviation. And remember, the standard deviation was 3.0. So here's what we're going to do. We're going to go ahead and go back to StatCrunch, and we're going to do a stem plot. So we have these here. We can go ahead and close this for now. All right, so we're going to go to graph, and we're going to pick stem and leaf. All right. So here we have all right. Let's go back to our data. So notice that the mean is 13 units, right? So lie within one standard deviation. So we know that x bar plus s is going to be 13 plus 3, which is 16, and x bar minus s is going to be 13 minus 3, which is 10. So we're basically going to find out how many observations are in that interval, right? From 10 to 16. So we'll go back to our graph now. Okay, so we'll go ahead and go to graph and then to stem plot. And we will go ahead and graph it. And now we're going to count all the observations from 10 through 16. So 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 2, 4, 6, 8, 32. So now we want to see, you want to count the actual number of observations and see what percentage of 42 that is, right? So now we're going to take that 32, which we just found. We're going to divide it by, or was it 36? I think it was 36, right? Divided by 42. Now, remember, that's going to be in decimal format. So if you want to turn it into a percentage, you're going to go ahead and multiply that by 100. Oh, not like that. You always have to be careful to come out of that. So times 100. So you can see if you round this to the nearest integer, we get 86%. So let me go ahead and clear that. Compare that to the result found in part C. Of course, the empirical rule was not exactly giving us the perfect answer here. The percentage estimated by the empirical rule is 8, basically if you just subtract 68 from 86, you see that it's 18 points less than the actual percentage, right? So the reason, of course, that happened is because, as you recall, it was not perfectly symmetrical, right? So, we were just trying to get an estimate for it. Student concludes that the mean and standard deviation in part B describe the center and spread of the number of units of all students enrolled at the college. And what would you tell the students? Well, remember that this would be a sampling bias, right? Because that particular author's sample may not be representative of the entire college, so the assumption would be incorrect. So anyway, it was interesting that we did this bit because, it tells you want to be careful. The best, distributions for the empirical rule are the ones that are really very close to symmetric. Okay. All right. So I think that should pretty much get you through the section. Okay. Should be enough information for you. And so stay safe till our next video.